Hello, everybody. Hi. I'm Andre Rosas. I'm an application engineer at GEA, Refrigeration Germany. This is Ron Hoffmann, my colleague. He's a product manager for screw compressors. And today I want to show you how semi-hermetic compressors can simplify the switch to ammonia. So first of all, why do we want to switch to ammonia? We've seen in recent years that the fluorinated synthetic refrigerants have become more under pressure, and it's been incrementing more and more in recent years. In 2014, the European Commission released the F-gas regulation, which, as you can see, tells the companies in the European Union to phase down their usage of fluorinated gases, which is measured by a CO2 equivalent, and this is done by steps. In 2022, the European Commission, they met again and they released a tightening of this regulation. And now, as you see, the step that was meant to happen in 2027 has now been pushed back to 2024. So we see the pressure is increasing more and more. Another source of potential pressure is the possible regulation of PFAS. These are other substances, and there are refrigerants which are part of this substance group, which has been found out to be potentially environmentally unfriendly. And so it is very possible that these will be regulated as well in the future. The high GWP, so global warming potential refrigerants, but also the low global warming potential refrigerants such as HFOs as well. And another source of further pressure is the striving of the companies to have a better image in the public eye, to look more green, more sustainable. And this, of course, generates more driving force to make the change to natural refrigerants. Why do we like ammonia so much? Ammonia is one of the most efficient refrigerants in the market. It is, because of this, a safe and sustainable choice for the future. And it is typically around 15 to 20% more efficient than direct expansion R404A refrigerant system. It has very good heat transfer potential and properties, and this makes the use of smarter equipment possible in the refrigeration system. It is an environmentally friendly refrigerant. It has a global warming potential of 0, and also an ozone depletion potential of 0 as well. And ammonia, as we know, is toxic, and at certain concentrations it can be flammable. So ammonia systems are always designed with safety in mind. And let's say the good thing is that we have an inbuilt detection system of ammonia. We can smell ammonia very, very low concentration, so leakages are, let's say, detected early. So what is the existing solution in our industrial refrigeration world? It's the open type compressor, and we use it because it has several benefits. First of all, it is a very flexible solution. You can really optimize each individual component. It is easy to service. You can access each component individually, for example, the motor. And it is a very highly efficient solution. That's why we use it. We will see later on, but when you compare it to the semi-hermetic compressor, this solution doesn't suffer from the suction gas superheat because the motor is outside of the compressor housing. So now we have the semi-hermetic solution. As we see, now we don't have the separation of the motor and the compressor. The motor is integrated inside the compressor housing. This means we eliminate the shaft seal, and this means there is no risk of shaft seal leakages. Oops. It is user-friendly, as we will see also further on in the presentation. It is easy to operate and to maintain. And due to the high level of integration, it is very compact. It has a small footprint. It is easy to integrate into multi-pack arrangements. And when you design it, let's say, properly with some considerations, it is also a very highly efficient solution. So before going further into detail, I'll tell you a little bit about the compressor concept. As I mentioned before, the motor is inside the compressor housing. On this side, we have the suction connection. The gas is sucked in through here and through the suction filter. It goes through the housing and through the motor towards the compression chamber where we have the rotors, and then out the discharge side on this side. So as we see, we call this the service side. because there are components which we want to access easily and they need to be maintained, such as the suction filter and the oil filter. We also have the terminal box, the oil heater, and the linear displacement center on this side. And also integrated inside the compressor, we have an oil stop valve, an integrated overflow valve, and a check valve on the discharge side. On the other side, we have what we call the connection side. So here we have the two main connections, the suction side connection and the discharge side connection. We have a centralized oil port for the oil connection, and the oil is distributed internally in the compressor. And here we have the optional economizer port, the optional liquid refrigerant injection port, and also the oil return port. So we, as the GEA, we come from an industrial background, and thus we also had to integrate our industrial philosophy into what is a more traditionally commercial solution, the semi-hermetic compressor. This means we have a variable VI inside our compressor, which is adjustable steplessly. The speed is regulated, the capacity is regulated via speed. We have a high-speed motor in the compressor, but we also have a capacity slide valve. And there is the injection oil flow towards the compressor rotors is adjustable. This means we can adjust the discharge pressure, temperature of the compressor. And as we come from an industrial background, there's a very robust, reliable design, which is not meant to be a throwaway compressor, but our industrial solution for the market. We will see also further on that it is an easy to maintain compressor. So there are some things which we have to take into consideration when talking about semi-hermetic compressors. As we saw before, the motor is integrated in the compressor housing. This means the gas is sucked in through the motor windings, and while cooling the motor windings, it takes heat and the temperature increases, so we have a superheated gas, and this has a negative impact on the efficiency of the compressor. And generally, semi-hermetic compressors have a simplified build. They don't have a variable VI, they have a fixed VI, and it's also very limited. So what are the possible solutions to this? These are solutions that we took into account for our compressor, the compacts. We restricted the range of application, so we focused on higher evaporation temperatures up from minus 20 degrees evaporation, and we optimized the efficiency for this range. This means we took a high-speed motor which can run up to 6,000 RPM. It's a permanent magnet motor, and as I mentioned, the variable VI, which we'll see in the next slide. So this is the application range from the complex compressor. We see it is somewhat limited, but we have implemented a variable VI from 1.8 to 5.0. This means we cover a wide variety of conditions, and we can guarantee the best efficiency at these conditions. And as I mentioned before, there's a high efficiency permanent magnet motor integrated in this compressor, which runs up to 6,000 RPM, and it needs to be inverter driven, so we can regulate the capacity of the compressor with this high-speed motor while being very efficient. Now let's talk about the maintenance of the compressor. We only need a yearly check of two components, the suction filter and the oil filter. And after that, there is only a major overhaul needed after 55,000 hours of operation. And this is, we think, a very good thing to have in mind, because this means we require less maintenance for standby compressors. Also very important, we integrated a triax bearing arrangement. This means the bearings, they last throughout the whole lifespan of the major overhaul lifespan of 55,000 hours. So there needs to be no regular checks done on the bearings. And as I mentioned before, there is no shaft seal in this compressor arrangement. This means there is no maintenance needed on the shaft seal. As I said before, all of this leads to less care for standby units. This is very beneficial for certain applications, and also lower maintenance costs. We just have two components which we really need to take care of yearly. We need to check them and eventually change them. And apart from that, just the major overhaul. Let's talk about the operation of the compressor. Regarding the sound and the vibration, as I said, the motor is integrated in the housing. This means it is cooled down by the suction gas and thus doesn't need an external cooling method, no fan. This lowers the sound emissions from the compressor. We also have a sleeve axial bearing arrangement, which absorbs vibrations from the compressor. And as we know, a vibration is equal to sound emissions, so this is also another factor that really benefits the sound emissions. And finally, this whole combination leads to around a 6 dB lower sound noise level from this compressor compared to an open type arrangement. 6 dB, to make it more understandable, it's around 50% decrease of sound, of noise in the human ear. So it's really a noticeable change. So now let's talk about the efficiency of the semi-hermetic complex compressor. Here we are comparing the semi-hermetic complex 400 against an equivalent open type compressor, our HM open type screw. And we're comparing them at minus 10 degrees to 45 degrees condensation temperature. They're both inverter driven. The complex runs up to 6,000 RPM and the HM up to 4,500 RPM. As we see here on the full load, let's say capacity, we see that the open type compressor is indeed a little bit more efficient than the complex. This is due to the fact that we have larger rotors, and this generally means higher efficiency when the rotors are bigger. But what we do notice is that the efficiency falls off rather quickly at around 65% part load, and while the complex maintains a very high efficiency down to around 50%, because we have the high-speed motor running at 6,000 RPM, so we can regulate it down to 3,000, and it's still running really efficiently at this speed. Now, if you take another comparison point, now we have increased the evaporation temperature to 5 degrees Celsius and the condensation to 50. Now we notice that the semi-hermetic is even more efficient than the open type competitor, let's say, at this condition. This is due to the fact that at these higher evaporation temperatures, the effect of the suction gas superheat is not as big as it would be on this condition. And so even here, we see that the complex is really optimized for these high temperature, evaporation temperature conditions, while still maintaining a very high part load efficiency. It is very easy to integrate into multi-pack arrangements. And multi-pack arrangement is an arrangement of several compressors on the same oil circuit, on the same oil system. So we have one oil separator, one oil cooler, and one oil filter with 2 compressors in this example. And this provides more flexibility. We can really, depending on the loads that we have, really vary the capacity of this arrangement. We have really high efficiency in part load, so this is really a good solution for part load conditions. And it's a redundant solution, so if for any reason one compressor falls out, it gets damaged, it needs to be serviced, there's still, let's say, 50% of the whole capacity available. Here we have 2 examples of our semi-hermetic complex in 2 multi-pack arrangements. On this side, on the left-hand side, there's a triple pack arrangement, so you see 3 semi-hermetic compressors with 1 oil separator, 1 shared oil circuit. And on this side, we have a chiller with a dual pack arrangement, so 2 semi-hermetic compressors and their chiller skid with the heat exchangers integrated. And now, if we compare an open type single compressor arrangement to a semi-hermetic multi-pack, we see it really now shines in the part load operation. At full load, again, we are comparing it to a bigger screw, so the efficiency is higher, but we see that the open type compressor falls off at around 60, while the semi-hermetic arrangement maintains a very, very high efficiency. Let's say the highest efficiency at down to 25% part load. This is due to the fact that at 50% we would shut off 1 compressor. We still have 1 compressor running at 6,000 RPM. And then this one we can regulate down to 3,000 RPM, which would correspond to this 25% part load position. Now let's summarize what we have seen today. The compacts, the semi-hermetic compressors in general are safe. They don't have a shaft seal, and thus they don't have the risk of having shaft seal leakages. The operation, as we have seen, is very easy. It requires low maintenance, has low maintenance cost, less care for standby units, and it has very noticeable reduced sound emission levels. It is a very compact. It's a highly integrated product. It integrates the motor and also other components. So it is very compact. It is easy to package into multi-pack arrangements, as we have seen. And thus it has also a very low footprint for, let's say, smaller machine rooms. And finally, we have seen that it can also be a very, very highly efficient solution for the industry. We have integrated the high-speed motor. It runs at 6,000 RPM, so we have very high part load efficiency, down to 50% with one single compressor. And the wide VI arrangement from 1.8 to 5.0 really guarantees very good adaptability to a wide range of applications. So this is it. Now, if you want to ask some questions, me and my colleague Ron will be happy to answer them.
Yes. Yeah, so if there are no questions, time is almost over. You find us in the hall 7, booth 512. And if you want to drink a beer with us, we have a nice booth party this evening. Feel free to join us.
Fantastic. Thank you.